Jai Hind students, welcome to my YouTube channel. Students, always be a student as long as you still have something to learn, and this will mean all your life. That is, there is no end to learning, isn't it? And students, study like there is no tomorrow, because if you keep putting off your studies for tomorrow, you will probably be too late then, right? So basically students, education is not a safety net. It is the rocket which will propel you towards success. I repeat, education is not a safety net. Instead, it is the rocket which will propel you towards your success. All you have to do is to have an aim and work on everything that takes to get a lift off. Right? So I hope you will definitely follow these guidelines. Right? So let's start today's session. Today we are going to discuss a very interesting topic, and which is the most important topic of this particular chapter of friction. I am talking about the laws of friction. These are the laws, these are the points which have been concluded after performing various experiments and observations, right? We are already aware of friction. We have done it in the previous lecture. Friction is an opposing force which comes into existence whenever a body moves, rolls, or tends to do so over the surface of some other body, right? Then we have discussed various examples, students. Like on a soapy floor, we tend to fall, isn't it? It becomes slippery because on a slopey surface, the friction gets reduced. Then we have also discussed skating on an ice rink is much easier, and actually it is effortless as compared to the skating on a road surface, right? It's again because of the fact that friction on an ice rink is very less as compared to the friction offered by the road surface. Then students, it is much easier to hold an earthen pot, and if you try to hold a greasy glass, then it will tend to fall down, isn't it? Because greasy glass, it offers very less resistance or less friction. So basically what I mean to say is that, students, the force of friction, it does depend upon the nature of the two surfaces in contact, and obviously their state of roughness. We have discussed in old view that if we consider smooth surfaces, then it tends to offer less friction. Suppose accidentally if we put our foot on a peel of banana, then obviously we will slip and definitely we are going to fall, isn't it? As the friction gets drastically reduced, isn't it? So this is the first law of friction. That is, frictional force, it depends upon the nature of the surfaces in contact and the state of their roughness. So I'll write it down. So this is a very important point, and which we can easily conclude with the help of several observations, isn't it? So force of friction depends on the nature of the surfaces in contact. It depends upon the nature of the surfaces in contact and their state of roughness. Right? So this is the first law. So again I repeat, students, different surfaces offer different friction, isn't it? It depends upon the pair of surfaces which are in contact, right? So force of friction does depend upon the nature of the surfaces which are in contact, and also it does depend upon the state of their roughness. Clear? Second, as we have discussed, students, frictional force is always of opposing nature. That is, it always acts in a direction opposite to which the body tends to move. If the body under the influence of some pulling force tends to move towards right, then force of friction will act towards left so as to oppose the motion of the body. Right? So, force of friction is always of opposing nature. It always acts in a direction opposite to which the body tends to move. And it always acts tangential. Tangential means, students, it always acts parallel to the surfaces in contact. Right? So that's the second law. So, force of friction is of opposing nature. It is of opposing nature. That is, it always acts in a direction opposite to which the body tends to move. Moves or tends to move, right? And it acts tangentially. That is, parallel to the surfaces in contact. Parallel to the surfaces in contact. So this is, students, the second law. Right? I'll elaborate this with the help of a diagram. Suppose, students, let's consider this diagram. This is a tabletop. Let us assume this to be a tabletop. And a block is kept over here, like this. This is a block. This is a block which is kept over a tabletop, right? Let us assume this is a tabletop. Let us assume in this direction it is pulled. That is, this is the applied force. Right? So, the block will tend to move along the direction of the applied force. Isn't it? So, therefore, force of friction, this is the two surfaces in contact. Force of friction, it will act tangential, that is, it will act parallel to the surface and in a direction opposite to which the body tends to move. So, small f, this represents force of friction. This represents force of friction or frictional force. Clear? And this is the applied force. We will represent the applied force by capital F. Understood, students? So, whenever a body moves or it tends to move, then force of friction does comes into existence. If the body remains static, then the force of friction that exists between the two surfaces in contact will obviously be known as static friction. And if the body actually starts moving, then also force of friction comes into existence. But that force of friction that exists between the two surfaces in contact when the body actually moves, that is known as kinetic or dynamic friction, right? But in both the cases, whether we are talking about static friction, limiting static friction, kinetic friction, it always acts in a direction opposite to which the body tends to move. And another point to be noted is that it always acts tangential, that is parallel to the surfaces in contact, right? I'll elaborate with the help of another example. Let us consider this to be an inclined plane, right? This is an inclined plane which suppose makes an angle theta with the horizontal. And suppose this is a block over here. This is a block. Obviously, this block which is kept on the inclined plane will tend to slide down, isn't it? It will tend to move along this direction. It will tend to move along this direction. So as a result, force of friction, which is of opposing nature, will tend to oppose its motion so as to act in a direction opposite to which the body tends to move, and it always acts tangential, that is parallel to the surfaces in contact. These are the two surfaces which are in contact, isn't it? So frictional force must act parallel to the surface in contact and in the direction opposite to which the body tends to move. The body tends to move along this direction, down the inclined plane. So the frictional force or the force of friction will act tangential, parallel to the surface in contact and up the inclined plane like this. Small f, it represents the frictional force, right? So I hope students this is very clear. So the first law is force of friction depends on the nature of the surfaces in contact and the state of the roughness. Second law is force of friction is always of opposing nature, that is, it always acts in a direction opposite to which the body tends to move, and it always acts tangential, that is parallel to the surfaces in contact, right? Okay, third one. Students, before we discuss the third law, which is very important, right? I would like you to know certain facts. Like, what we'll do is, we'll study about the normal reaction, its relationship with the weight. For example, in this case, students, imagine this condition, right? In this case, the block is lying horizontally on the tabletop. It is lying horizontally. So, here, the weight of the block is exactly balanced by the normal reaction. This is the normal reaction, isn't it? Normal means acting perpendicular to the surface on which the block is placed. Here, reaction is equal to the weight. Clear, students? So here there is no problem. Here reaction is exactly equal to the weight provided the body under consideration is placed horizontally, as in this case. And we will see that if you increase the weight, the normal reaction will also tend to increase accordingly. Suppose if another identical block is placed over here, like this. So weight of the system will become 2W. It will become twice. So accordingly the reaction will also now become twice. So what I mean to say is that with the increase in the weight of the system, if it is placed horizontally, the normal reaction will also increase accordingly, so as to balance the weight, isn't it? So here, weight is equal to the normal reaction, provided, mark my point, provided the body of the system is placed horizontally, right? So here we'll discuss that force of friction, it increases with the increase in the weight of the system. We'll discuss it, right? We'll discuss through some experiment. Now, in this case, students, suppose this is a wall, it's a vertical wall. Okay, a block is pressed against this wall. This is a block. This is a wall, and a block is pressed. Its weight will act in the vertically downward direction. So obviously, it will fall down, isn't it? Here, weight will have no role to play in the friction. Here, weight, I repeat, here in this case, the block is not placed horizontally, it is placed in this manner. In this case, the weight of the block will have no role to play in the force of friction, right? Now, it will be in its position if we push the block against the wall. So therefore, this wall will exert an equal and opposite force on the block in the opposite direction, and that is known as reaction. This will be the reaction. This will be the reaction. So force of friction, this force of friction which will exist between the two surfaces in contact and will act tangential, and it will oppose the motion of the block. This body will tend to fall downward, so force of friction will prevent the block from falling downwards, right? But in this case, the force of friction is due to the reaction. which is exerted by the wall on the block. Force of friction doesn't depend upon the weight in this case. Understood? So whenever we say force of friction is directly proportional to reaction, so it will be more appropriate to use the term normal reaction instead of using weight. Here weight is equal to the normal reaction, isn't it? But here weight doesn't play any role in the friction. So while studying friction, we always make use of the term normal reaction instead of weight. Clear, students? So before we discuss further, we will try to verify the fact that force of friction is directly proportional to the normal reaction. For blocks placed on the horizontal surface, force of friction is directly proportional to the weight, and weight is equal to normal reaction. So we can conclude this, right? But for any other cases, like in this case, force of friction is directly proportional to normal reaction. So this statement is always valid. So instead of writing weight over here, you should use the term normal reaction so as to be applicable in both the scenario. Right, students? So before we discuss this any further, before I write down the statement of the third law, I must request you to watch this short video. It's a very interesting video, and this can be definitely done by you all in your respective physics lab, right? This is a video related to the experimental verification of the fact that force of friction is directly proportional to the normal reaction. So please watch this video with full concentration, right?
Let us consider a block of weight, say 2 Newton, and let it be attached to a spring balance. And students, ensure to make the block move at constant velocity. Now, when the block is moved at constant velocity, uniform motion, then the block must be under the influence of balanced forces. So in that case, the pulling force must be exactly equal to the force of friction. So that gives a way to measure the friction force. Now suppose a block of 2 Newton weight is made to move with constant velocity, and let the spring reads 0.5 Newton. Now place another identical block, and now the system weighs 4 Newton. Now the spring balance reads 1 Newton. Similarly, students, now place third identical block. So total weight of the system will become 6 Newton, and now it is observed that the spring balance reads 1.5 Newton. And on introducing the fourth block and making the system to move in uniform motion, now the spring reads 2 Newton. So if you plot a graph between the pulling force, which gives the measure of the force of friction, and the weight of the system, which was gradually increased from 2 Newton, 4 Newton, 6 Newton, 8 Newton, then we will observe a chart to be obtained as shown. Now let's plot the graph. Corresponding to 4 Newton, the force of friction, that is the pulling force, is found to be 1. Corresponding to 6 Newton, it was found to be 1.5 Newton. And corresponding to the force of 8 Newton, the force of friction or pulling force is found to be 2 Newton. So now if you join all these points, we will get a straight line, which indicates that force of friction is directly proportional to the weight. Therefore, students, force of friction increases with the increase in the weight. But wait, this is not the appropriate term to be used over here. Instead, we make use of normal reaction force. So a normal line is a line that is perpendicular to a surface. So let us draw a horizontal line, and then let's draw a perpendicular to this horizontal line. This line is known as the normal line. So a normal force is the reaction force of the lower surface to the upper surface. Now let us consider a rock to be placed on a flat surface. The weight of the rock obviously will act in the vertically downward direction. So as per the action-reaction concept, an equal force will be exerted by the ground on the rock in the upward direction. So that is known as a normal reaction force. Now since the rock is lying on the horizontal floor, therefore normal force would be equal to the weight. Now if additional force is applied in the downward direction, then the normal reaction will also get increased. So as a result, the normal reaction force is always equal to the weight, provided the weight is lying horizontally. Now consider a block to be pushed against a wall. Now here, the block will have its weight acting in the downward direction, but here the weight of the block won't play any role in the friction. Now the force with which the block is pushed horizontally against the wall. So due to that, a reaction force will be coming into play, and this is the force which the wall will exert on the body. So students, in this case, friction is due to the normal reaction force and not due to the weight. Therefore students, it is more appropriate to use the term normal reaction instead of weight. Therefore, we conclude that the friction is directly proportional to the normal reaction. Normal reaction is equal to the weight of the body only when the body is lying horizontally.
Okay students, through this video and through this experiment, we have experimentally proved the very fact that the force of friction between any two given surfaces is directly proportional to the normal reaction between the two surfaces. This is what we have experimentally verified, right? So this is the third law of friction. So mathematically, what we have verified is force of friction, that is small f, is directly proportional to the normal reaction, which is R. R is the normal reaction. R is the normal reaction. Now, as you are aware, students, I mentioned it very clearly. Actually, when the block is placed on a horizontal surface, then force of friction is found to increase proportionately with the increase in the weight. So, here F is directly proportional to W, but reaction is always equal to W in the case block is placed horizontally. So, it is more appropriate to use the term normal reaction. It is applicable in all the cases, whether the block is placed horizontally or it is placed vertically against the wall, isn't it? So, instead of using force of friction to be directly proportional to the weight of the system, it's not applicable in all the cases. We need to write force of friction to be directly proportional to the normal reaction, right? So, in order to eliminate this proportionality sign, we need to introduce some constant. So, this constant is mu. This is constant of proportionality and it is known as coefficient of friction. So, mu is constant and it is known as coefficient. It is known as coefficient of friction. And the value of coefficient of friction depends upon nature of the two surfaces in contact, right? It also depends upon the type of friction. Like when the body actually starts moving, then kinetic friction will come into play. In that case, mu is known as the coefficient of kinetic friction, right? In case even after pulling a body or even after the application of some external force, the body still doesn't move. So it means that the surfaces which are in contact, there must be some static frictional force. So in that case, the coefficient of friction would be static, coefficient of static friction. And in case the body is on the verge of motion, there we have discussed the magnitude of the static friction is found to be maximum. In that case, mu is known as the coefficient of limiting static friction, right? So, generalizing, we can say that the coefficient of friction is defined as the ratio of the frictional force to the normal reaction. So being the ratio of two similar physical quantities. This is frictional force, it is force, normal reaction, this is also force. So being the ratio of two similar physical quantities, it has got no unit. And as I have told you, this coefficient of friction, it depends upon its value, it depends upon the nature of the surfaces in contact, right? So for those surfaces for which the value of mu is low, it means that those surfaces offer low friction. And if the value of mu for the pair of surfaces is very large, it means that those surfaces offer very high friction, right? So let's proceed forward and discuss the last law, right? This is very interesting one, students. Again, experimentally we will verify the fact that the force of friction that exists between the two surfaces in contact is actually independent of the surfaces in contact as long as the normal reaction remains constant. So before I write down the statement, let us prove it experimentally, right?
We know that pulling force gives a measure of the friction force provided the system is made to move uniformly. Here, the four identical blocks are made to move with constant velocity, that is in uniform motion. Thus, the pulling force will give us the measure of the force of friction. Here, the surface area is made twice, keeping the weight constant. And in the very next experiment, the same four blocks are used. The weight is constant, but the surface area had been made thrice. And lastly, again, the four blocks are arranged in such a manner that the surface area of contact, it becomes 4 times, weight remaining same. In all the cases, the system is moved uniformly. That is, the pulling force will give the measure of the force of friction. Now, the reading shown by the spring balance is close to 2 Newton. Now, in case keeping the weight constant, the surface area is made 3 times. Still, the spring balance shows a reading close to about 2 Newton. So what we observe, keeping the weight constant and increasing the surface area, it doesn't affect the pulling force or the force of friction. In the last case, when the surface area is made quadrupled, that is, it is made 4 times, keeping the weight constant, still the spring balance, it shows a reading of close to 2 Newton. From the above experiment, we can safely conclude that the friction is independent of the area of surfaces in contact so long as the normal reaction, that is the weight, remains the same.
So students, what we have experimentally proved is that the force of friction between any two surfaces is independent of the shape or area of the surfaces in contact as long as the normal reaction remains same. So that is the fourth law. So these are collectively known as the laws of friction. Do remember the third and fourth one. We have experimentally verified these 2 laws, isn't it? So again I repeat the laws, student. First law is force of friction depends only on the nature of the surfaces in contact, right? And their state of roughness. Second is force of friction is always of opposing nature. It will always act in a direction opposite to which the body tends to move, and it always acts tangential, that is parallel to the surfaces in contact. Third one, which is very important one, and it has been experimentally verified, right? And these are the 2 laws which can be experimentally verified. I will suggest you all to experimentally verify the last 2 laws in your respective physics lab, right? So third law is the force of friction is directly proportional to the normal reaction. And fourth one is the value of the force of friction. it is independent on the area of the surfaces in contact. It is independent of the shape as well as the area of the surfaces in contact. As long as, this is important, as long as the reaction remains constant. Right? In the horizontally surface, when a block is placed or a system is placed on a horizontal surface, then the reaction is equal to the weight. So, in the last case, as long as the weight of the system remains constant, the force of friction is independent of the area of the surfaces in contact. Right? Okay students, now let us discuss about these two topics, angle of friction and angle of repose. Let's start with the angle of friction. Right? Let us consider this to be a block of mass m, say, and it is lying on a horizontal surface. Right? So suppose this is the direction of the applied force. This is the direction of the applied force. So students, obviously force of friction being of opposing nature, it will tend to oppose the applied force. Right? So it will act in a direction opposite to which the body tends to move. So the body will tend to move along this direction. So the force of friction will act along this direction, parallel to the two surfaces in contact. So this force I am drawing at this particular point. Right? So this is, suppose, the frictional force. It is represented by small f. It is the force of friction. Right? And then it will exert a force on the tabletop. The tabletop will exert an equal and opposite reaction force on this body, which is known as the normal reaction. This is the reaction force. Right? So let us find out the resultant of the frictional force and the normal reaction. Now look friends, these are the two vectors representing the two adjacent sides of a parallelogram. So their resultant would be given by the diagonal of the parallelogram passing through the same point. Right? So the resultant of this frictional force and the normal reaction is represented by the diagonal of the parallelogram passing through the same point. So suppose this is the resultant. This is the resultant. Right? So this is a parallelogram. These are the two vectors representing the adjacent sides of a parallelogram. So the vector resultant is given by the diagonal of the parallelogram passing through the same point. So Fr, it is the resultant of frictional force and the normal reaction. Now students, angle of friction is the angle which this resultant force makes with the normal reaction. So this angle, let us denote it by alpha. So this angle alpha is known as the angle of friction. So I'll write down the definition over here. Angle of friction is defined as the angle which the resultant of frictional force and the normal reaction makes with the normal reaction. So this is the definition of angle of friction, right? This angle, this is the angle which the resultant of force of friction and the normal reaction makes with the normal reaction. So this angle, which is represented by alpha, is known as the angle of friction. Now students, it's a right angle triangle. This is acting horizontally parallel to the surface in contact, and this is the normal reaction acting perpendicular in the upward direction. So this angle is 90 degree. So this is also 90 degree. So if you consider this triangle, we get tan alpha. It is equal to perpendicular by base. So this would be equal to F. This is a parallelogram. So the opposite sides are equal, isn't it? So this is F, this is R. So tan alpha would be perpendicular by base. Clear students? Also we are aware, we have discussed the laws of friction. So we are aware that if mu be the coefficient of friction of the two surfaces in contact, then the coefficient of friction is also defined as the ratio of the frictional force to the normal reaction, that is F by R. So from these two students we conclude that mu is equal to tan alpha. So this is an important relationship. So the coefficient of friction is numerically equal to the tangent of the angle of friction, right? So this is coefficient of friction and this is tangent of angle of friction, right? So put this as equation A. So students, angle of friction is the angle which the resultant of frictional force and the normal reaction makes with the normal reaction. And tan alpha is F by R. Also, as per the third law of friction, coefficient of friction is ratio of the frictional force to the normal reaction. So equating these two, we get the coefficient of friction is numerically equal to the tangent of the angle of friction, right? Now let's discuss angle of repose. It's again a very interesting topic. Suppose students, this is an inclined plane. It makes an angle, suppose theta 1 with the horizontal, and a block is placed over here of mass m. And suppose this block remains at rest, it do not slide, right? On increasing this angle theta, it is the angle which the inclined plane makes with the horizontal. So on increasing the angle, a stage will come where the block will just begin to slide. Here theta 2 is, this is A, this is suppose B, and this is C. Here theta 2 is greater than theta 1. Suppose when the angle is increased from theta 1 to theta 2, still the block doesn't slide. Now let us consider the angle which the inclined plane makes with the horizontal be further increased. Suppose at angle theta, the block placed on the inclined plane just begins to slide. Then this angle is known as angle of repose. So students, how do you define angle of repose then? So angle of repose is defined as the angle which the inclined plane makes with the horizontal, at which an object placed over it just begins to slide, right? So let's try to find out the relationship between the angle of repose and the coefficient of friction, right? Okay, what are the forces acting on it? One is its weight. If its mass is m, then its weight would be mg. The other is the reaction force. It will be along this direction. This is the reaction force. It will always act perpendicular to the surface over which the body is placed, right? Now the body will tend to slide along this direction, isn't it? It will tend to slide along this direction. It will tend to slide. It will be on the verge of motion. So force of friction will act in the opposite direction. So this is the force of friction, F. Now what you do, students, mg can be resolved into two components. One in a direction opposite to the normal reaction, like this. So we are aware, if this is theta, this angle would be also equal to theta. So let's resolve mg into two perpendicular components. This component would be mg cos theta, while the other component, which is opposite to the frictional force, this component would be mg sin theta. Right, students? Now since the body is on the verge of motion, it just begins to move. Therefore, the body may be considered to be under the influence of balanced forces, isn't it? Therefore, R should be balanced by mg cos theta and this frictional force F should be balanced by mg sin theta. Therefore, mg sin theta, it should be equal to small f, and mg cos theta, it should be balanced by the normal reaction. So students, combining these two, if you divide these two, right? If you divide these two, what we get? mg get cancelled. Sin theta by cos theta, that will give us tan theta. It is equal to F by R. Right? Also, if mu is the coefficient of friction between the two surfaces under consideration which are in contact, then coefficient of friction, we are aware, it is defined as the ratio of the force of friction to the normal reaction. Therefore, students, combining these two, if you consider this to be 1 dash and this to be 2 dash, so combining these two, what we get? Mu is equal to tan theta. So, the coefficient of friction is also numerically equal to the tangent of the angle of repose. Here also, the coefficient of friction is numerically equal to the tangent of angle of friction, and here we have obtained that the coefficient of friction is numerically equal to the tangent of angle of repose. Right? So, in order to find out the relationship between the angle of friction and the angle of repose, we will consider equations A and B. So, what do we get? From equations A and B, what we get is tan alpha is equal to tan theta, which implies that alpha is equal to theta. So this is an important result. So the angle of friction is numerically equal to the angle of repose. Right, students? So before we conclude, let's revise the topic. Angle of friction, as I stated, students, it is the angle which the resultant of the frictional force and the normal reaction makes with the normal reaction. Right? And what is angle of repose? It is that angle which the inclined plane makes with the horizontal, at which an object placed on it just begins to move. That is, it is on the verge of motion. So that angle which the inclined plane makes with the horizontal is known as angle of repose. And mathematically what we have derived is the angle of friction is always equal to the angle of repose. The coefficient of friction is equal to tangent of angle of friction as well as the coefficient of friction between the two surfaces under consideration is numerically equal to the tangent of angle of repose. Right? So students, I hope you have enjoyed this session. Do practice and do revise all these topics thoroughly. Right? So that's it for this particular session. Do join me in my next lecture then. Till then, thank you and have a very nice day.